Use Ricardo Lima. Ricardo Lima is a researcher at KAUST. Dr. Lima works in the Extreme Computing Research Center, where he works with Professor Neo. He made significant contributions to the fields of process systems engineering, optimization, energy, and renewable energy systems. So with that, I'd like to introduce him to his talk, Stochastic Optimization for Virtual Power Plants and Network Constraint Unit Commitment Integer Optimization Problem.
Yes.
So, okay.
Thank you very much for the introduction, and thank you for the invitation to be here. Once I took a workshop for doing presentations for jet lag people when you go to conferences, and maybe I have to take a workshop now for the last session of the day, where people are tired. So today, what I'm going to talk first, I'm going to talk about two different problems. And the first problem is a problem that relates with the virtual power plants. And what is a virtual power plant? A virtual power plant is an aggregation of distributed energy resources. For example, a thermal plant, a solar farm, and a wind farm that will participate as a single entity in the electricity market. They can also support some transmission management. This is a type of problem that has been in the news for some time as a solution to solve problems related with the power network. So you see that they discuss if the power plant or the VPP will solve some of the problems. You see that Tesla is building, of course, the largest VPP in the world. And if you go to some geek sites, you can see also some definitions of VPPs. And basically here, what you see is that what the VPP is a group of different entities that they play in the power system. And what you try to do is to manage all these distributed plants or units that are distributed across a country. In our case, what I'm going to do here, we are going to compare two different approaches to solve a risk-averse problem for VPPs. We are going to compare risk-averse stochastic program and adaptive robust optimization. And I will go through the problem statement, the formulations, the methods, and some results. So in our case, we are considering a small VPP, and that comprises of a wind farm, a pump storage hydro unit, and a thermal unit. The characteristic of this hydro unit is that it can buy or sell it can consume or produce electricity. So if the price is low, for example, it can buy and store water to sell when the price is higher. And this VPP will interact with the electricity market by selling and buying electricity in the market pool at a time resolution of 1 hour, and it will establish contracts to sell the energy. And so the problem that we are trying to solve here has a time horizon of 1 week. So we are going to solve this problem for 1 week with a time resolution of 1 hour. And the type of problem that we are solving, we have two types of decisions. We have first stage decisions and second stage decisions. The second stage decisions are also called recourse decisions. And so how does it work? Before the week starts, we solve an optimization problem that is basically a self-scheduling problem and a forward contract. And so before the week starts, we are determining when the thermal unit should be on or off during the week, and what contracts we should sign to buy or sell electricity at a fixed value and fixed amount of energy during the week. The second stage decisions are, for example, how much power we are going to produce with the thermal unit when it is on, and how much we are going to produce with the pump storage or consume, and how much we are going to buy and sell to the market in the pool. So in fact, when we solve this problem, we are interested first only on the commitment of the thermal unit and on the contracts. We fix those decisions for the week, and then during the week, we are going to solve again this problem with a short-term forecast every day to decide the actions of this pump storage and this thermal unit according to the prices of electricity in the market. So in this problem, the profit is a random variable, and we have these X that are first stage decisions that are related to the power or the energy that we are going to buy and sell through contracts. We have the cost of startup, shutdown, and commitment of the thermal units. And then here we have the terms for the power that is sold in the market or bought. And we have also some variable costs of the power generation of the thermal units. So basically, the formulation looks like this. We want to maximize this profit, right? Subject to the constraints on the contracts, the logical expressions for the startup shutdown of the thermal unit, and all the constraints of the thermal unit, plus the energy balance, the operation of the pump storage hydro unit. And the uncertainty comes on the wind power here on the energy balance. And it comes also on the electricity price, because we don't know what is going to be the electricity price during the week. And we also have uncertainty on the wind power. And based on that, you have to determine when the thermal unit is going to be on or off the contracts. And also you take decisions when you are going to buy or sell electricity in the pool. Yes.
So, you have the random variable enters in the objective function and all inequality constraints.
Yes.
Okay, and the JR, what is that inequality constraint?
This is an equality constraint that is related with the operation of the hydro plant. You see, it is R. It does not have any cost, but there is a small detail that I'm going to explain here. That is what are the second stage variables and how they relate with the uncertainty. But let me come to that. So basically, we have a formulation of this type, right? So you are trying to maximize a function that is maximize a variable that is the profit. The profit is random, and we are going to see different versions for this function here, subject to these constraints. Here in this formulation, it captured this two-stage decision process. So these X and Z are the first stage decisions that you take before the uncertainty realizes. And then as the certain parameters, they realize, you take decisions that are these Y decisions. So depending on the electricity price on the wind, you are going to take these decisions, okay? No, in fact, people do multi-stage, right? So you could do the first stage is before, the second stage is the Monday or the Sunday, Tuesday. So, but what we do, in fact, is we approximate all the decisions in 1 week for the second stage. So in this problem, you get the commitment of the unit and the contracts, and then every day you have to solve again the same problem with that fixed. But if you can handle the problem in a multi-stage that becomes more complex, then people do multi-stage. But here we are just approximating all the decisions of the week to this second stage. So in this case of the virtual power plant, what we were interested in this work was what is the impact of these alternative functions for this variable of the profit? So in the stochastic programming approach, people usually maximize the expectation of the profit, or you can maximize the C-var of the profit, or in fact, you can maximize the combination of the expected profit and the C-var of the profit. But what we were interested was compare a stochastic programming approach using these type of objective functions with a robust optimization approach where you maximize the infimum of the profit. Both approaches in a two-stage decision process. So let me go to the stochastic program. So the stochastic so we have this original problem that we call our stochastic optimization problem. Of course, we can replace this by this expectation of the of the expected profit and C var of the profit. But what people do in stochastic programming approach is they are going to consider a sample of scenarios. So basically they consider a discrete probability distribution function, and they replace this problem by this problem here. So where here you calculate what is the expected cost or the expected profit of your second stage decisions, and you have multiple scenarios for this HW and for this CW. It's kind of, you pick a sample of scenarios and you plug in your expected value problem. So if you have a deterministic problem, the deterministic problem will look like this, right? And where this is the expected electricity cost, and this will be your expected wind. When you move to stochastic programming, what happens is that now you consider a sample of scenarios, and if the sample is large enough, then you kind of approximate the distribution. But at the end, this is just a deterministic problem, because you plug in the scenarios and then you have a deterministic problem, right? The thing here is that we have X as continuous variables and Z binary variables. And when you go from year to year, right, you are increasing the number of constraints considerably, because now you have this set of constraints for each scenario. And the interesting thing here is that the first stage decisions, they should be feasible for all the scenarios, right? And maximize the profit in expectation. This is completely different from solving one optimization problem for each scenario. When you do that, you assume that you have perfect information. Here we are solving for X that is feasible for all the scenarios that we postulated for our problem. Yes. So what happens is that you take only the X and Z as the decision, right? And then you will try to, so because next day you are estimating forecasting the wind. It has a smaller error, right? So you take a decision for that forecast, right? And then you take the decision and then you calculate what is your profit. That is what we do then in a sample average approximation. That is, we fix our decisions. We pick 30 samples of 2,500 scenarios, and we calculate an estimate of our expected profit and an estimate of the C var of the profit, and we try to see how good it was our initial X and Z for that week. Yes.
The constraint.
Yes. That we have. No. Yes. So the expectation, right? So the expectation is here on these profits. That is the profit of the second stage decisions, right? But you have to postulate a number of scenarios here. Right. So what we do, in fact, is we postulate 30 samples, each sample with multiple scenarios. Right. We solve the problem for each sample of scenarios, and then we calculate these estimates of. We calculate upper and lower bounds with statistic errors on the true optimal value of the profit. That is this value here. Right. So this is the stochastic programming approach, right? And then we have the robust optimization approach. In the robust optimization approach, now you are maximizing the infimum of the profit. And now, instead of using the discrete scenarios, as in the stochastic programming, what you use now are two uncertainty sets, where these two uncertainty sets are equal. So this variable H for the wind is equal to a forecast value plus an upper deviation and a lower deviation. So basically what we are doing is we are discretizing the uncertainty set in three values: the upper value, the lower, and the forecast value. So let me see if I give you a better example on this. So this is the point forecast, upper deviation, lower deviation. And there is a parameter here that is the risk control, that you can constrain the number of deviations from the point forecast. So if you are very risk averse, you assume that you may have lots of deviations and you want to take your decisions that maximize the profit, considering that the deviations may be large. So for the electricity price, how do we do this? We do a forecast with an ARIMA model, and then we use the 90% prediction error to build this uncertainty set, where the point forecast will be this parameter here, and then the upper bound and the lower bound of this of the 95% prediction error will be defined here as upper and lower deviations. And so in this kind of problem where you have 168 hours, you may have 168 deviations. So the maximum value of this gamma is 168. So if you put gamma equal to 0, that means that you trust your forecast. And so you just have a single forecast. If you don't trust your forecast, you put this equal to 168, and you assume that the electricity price may change. And the optimization will maximize the infimum of the price, considering that you can have the worst electricity price that can be at the forecast or at this point or at this point. Okay, so these are the formulations in a nutshell. And so how do we solve these type of problems? With the stochastic programming, we can solve the original formulation directly. It's just a very large problem, or we can decompose the problem. The robust optimization, we have always to decompose the problem because of the structure I'm going to show you. But how do we decompose the problem? So we pick the original problem and we create a relaxation of the original problem. And if you create a relaxation, and then you are maximizing, you get an upper bound, and then you have some subproblems. You pass the solution from the master to the subproblems. You calculate a lower bound if they are not equal or within a tolerance. Then you add a cut or a constraint to the master problem, and you iterate until they are close enough. So here we have the robust optimization versus the two-stage stochastic programming approach, where we here in the objective function we try to maximize the C-var of the profit. Okay, and so what happens here is that you are maximizing. So here I already decomposed the problem in two parts. So in this problem, the variables depend only on x and z, and then you have the infimum of r, where r is this problem here. So here you are maximizing the infimum of r, where r is the maximum of this. And we are going to use this here for the decomposition method. But what I would like to call your attention, C-var of the profit here, they are very similar, because here it is the infimum of r, but here in the case of the C-var, if you move alpha to the extreme, you have kind of also the worst case approach. So the way you decompose problem is very simple. So basically problem, and we are going to approximate this C-var using some outer approximation. And that is what we do here. A problem where we replace the C-var by W2, and then we have these constraints here that outer approximate the W2, and basically this is a relaxation of the original problem. And in the stochastic programming, what happens is that all the scenarios create a set of constraints that are independent, and so you can solve a set of independent problems for z and x that you obtain from the master problem. So you can solve the master problem, get z and x, solve these subproblems, and then add these variables, the dual variables, into the cuts, and these cuts will cut the previous solution. For the adaptive robust optimization, it is a little bit different. Instead of adding cuts that approximate the infimum of r, in fact, what we are going to do is we are going to add those constraints that are the constraints for each scenario. We are going to add them to the master problem for some specific realizations of the uncertainty that are determined by this problem here. From H and C, then they will come here and here, and these variables are copies of the original variables. So what our motivation was that, in fact, you may have a robust optimization formulation, but you can also have a stochastic programming formulation using the CVAR in the objective function. And what we know is that when alpha goes to 0, the CVAR goes to the expectation of f, and we recover the function where we have the expectation of the profit. But when alpha goes to 1, then you have the infimum of the profit, which is very similar when you do the robust optimization. So what we were curious about was what type of results do we obtain using both approaches, and how does computationally they behave. And of course, what happens is that in terms of risk parameters, when we do the stochastic programming, here the alpha is the quantile for the value at risk, and the beta is the weight of the expected profit and CVAR of the profit in the objective function. And in the robust optimization is just this gamma. And so the way we do this is we do some Monte Carlo sample average approximation to get the scenarios of the electricity price and the wind. And so what we did was 30 samples of different sizes and solve the problem multiple times just to get some values so that we can compare with the robust optimization. And so that is what I'm going to try to show you. There are here some details about the wind ensemble and the electricity prices. So basically these are the wind forecast, the forecast for the electricity prices, and this is the size of the problems comparing the stochastic programming and the adaptive robust optimization. But what I want to get is here. So here, what we have is a size of the sample n. This is the number of scenarios that we include in the stochastic programming, and these computational times are the average for 30 optimization runs with 30 samples of 10 scenarios, 50, 100, 500, and 5,000. And so what we see is that this case is when you are maximizing the worst profit with the stochastic programming. And what we see is that as the size of the sample increases, it becomes really difficult for the stochastic programming to optimize the worst profit. And now if we compare with the performance of the adaptive robust optimization, what we see is that the computational time, the wall clock time, depends on the budget of uncertainty. And when we project these times into the previous slide, this is what we get. So what we see is that stochastic programming with 5,000 scenarios in the problem, it's competitive with the robust optimization that just considers the worst case that can happen in those random parameters. Then what we did was we fixed the first stage decision, and we generated 30 replicas of samples with 25,000 elements to see how does the expected profit and expected and the CVAR, the estimate of the expected profit and CVAR of the profit, they behave. And we want to compare stochastic programming and robust optimization to see how does it work. So what we have here is this estimate of the expected profit and CVAR for one given solution for different risk parameters. And what you can see is that if you have a risk neutral approach, this is the expected profit. And as you become more risk averse, your expected profit decreases, but the CVAR of the profit increases, right? And this is what happens with the stochastic programming. And then with the robust optimization for different values of this budget of uncertainty, we can see that we have a similar outcome, and this is also for using the 30 samples of 25 scenarios to just evaluate. And so what we found was that for specific values of the parameterization of the risk with stochastic programming and robust optimization, in fact, we could get exactly the same first stage solutions And that translates in exactly the same estimates of the expected profit that you get, right? And but there were some other cases that it was different, okay? But using stochastic programming or robust optimization may lead you to the same results depending on the way that you parameterize the risk. And in the operations research community, there is a huge fight between stochastic programming and robust optimization, and we tried here to analyze both approaches. So the focus was on the comparison was on the formulations, on using efficient methods to solve these problems, and then on try to evaluate the computational performance of both approaches. So some conclusions. The stochastic programming is competitive if you solve all the scenarios in parallel, even though you may have 5,000 scenarios, versus in the robust optimization where you have only the worst case. The L-shaped method, the performance degrades when you go to the extreme, the worst scenario, and the performance of the CCG method, that is the method for the robust optimization, depends on the risk parameters, right? And so when we try to compare over efficient performance methods, different sizes of the sample for the stochastic programming, and different risk parameters. And what the conclusion was that, well, similar first stage solutions can be obtained depending on the way you parameterize the risk. Okay, so this case was a thermal plant, one wind farm, and one hydro pump unit. There is another problem that I think that is the most important optimization problem in the world. And why? Because this optimization problem is solved everywhere in any country, any state in the United States, several times per day, every day, and that determines how the power generation will be scheduled for the next day. And so what it does, it defines which hydro plants will work the next day, which plants of coal, gas, and nuclear. Well, the nuclear are most of the times constant, and it tries to meet the electricity demand. It tries to make supply equal to demand. And at this problem level, there is no market, only scheduling. This is a very large problem that is solved everywhere, every country, every day, multiple times per day. But this problem is mainly solved deterministically. And what we are trying to do is to solve this problem considering uncertainty in some of the parameters, right? So we consider uncertainty on the load demand, on the solar power, and on the wind. We have a stochastic program, and we try to get what is the optimum generation schedule for the next day. So, of course, this is a key task. Ensures that we have a secure and economically efficient supply that is critically important for everything in the society nowadays, right? There is no artificial intelligence if you don't have electricity, right? So what is the objective? So the objective is to maximize the social welfare, that is to minimize the electricity generation cost. And so if you consider the case of Saudi Arabia, where you can have a peak consumption of 50 gigawatts, and if you consider this cost of the energy, this is the cost per year in dollars, right? 1% away from the optimum, if you consider that this is the optimum, 1% away in terms of money is 600,000 per day. So this is a relevant problem to be solved, and it is a very large scale problem. It helps also to integrate the renewables and to reduce CO2 emissions. And what I'm going to show you are some results for a realistic case study. It is a case study that mimics the power system of Texas. And so these black dots are the nodes and the lines are the transmission lines. And the red dots is where you have demand. So the demand is distributed by the nodes. Not all the nodes have demand. You have a distribution of wind farms, of solar farms, thermal plants, hydro plants, and nuclear plants. And we have scenarios with 8, 20, and 40 elements for demand, wind, and solar power. It is a large scale, it has continuous and binary variables, and we have this uncertainty. So let's see an example on how difficult it is to solve this problem. First, in terms of size, if we don't consider the network, we have around 1 million constraints. When we add the network, it jumps like more than 22.5 million constraints. So, for example, in Europe, they solve the unit commitment problem, and then they try to figure out how the transmission net, how that solution will work on the transmission network, right? And you see also that the number of variables also jumps in kind of 1 million. The number of binary variables is the same because that is related with the thermal units. So the thermal units are the same without or with network. And so what is the impact of considering the transmission network in this problem? So without network and considering 8 scenarios, we can solve this problem in around 500 seconds to a gap of 0.001%. So this is, the gap is kind of a measure of the global optimality of the solution, right? But when we add the network, immediately after 10 hours, we get a gap of 37%. So the transmission network adds lots of complexity to the problem. Why? Because now the thermal units have to be scheduled in such a way distributed by the network that the energy can flow through the network respecting the Kirchhoff laws, okay? So when we try to solve these with 20 scenarios and 40 scenarios using the extensive form, that is the full formulation, after 10 hours, we cannot get one solution from Cplex that is a solver from IBM for this type of problems. And if we use commercial Bender's decomposition from Cplex, from IBM also, after 10 hours, we cannot get one single solution for this number of scenarios. And so this was the challenge that we had, is like, can we get solutions for 20 and 40 scenarios?
What do you mean is you cannot find a feasible point?
You cannot find any feasible solution. Yes,
Does
that
not
means
even to minimize the objective function, just
no.
feasible solution.
So yes, so what happens here most of the times is that you have to solve the linear relaxation of the problem. And because of the size of the problem, it takes like almost 10 hours to solve the linear relaxation. And if you know something about branch and bound, if you have an LP problem that takes 10 hours to solve the relaxation, when you go to the branch and bound and you are going to solve one LP problem at each node for each combination of binary variables, it will never happen, right? So, but here it is with the decomposition algorithm, right? So even at this stage, we cannot find one integer solution. So what is the problem statement of this problem? Given is the demand forecast for each node that has demand, the wind and solar power forecast for each node where we have this type of farms. We know the transmission network features. We know all the characteristics of the thermal units, and these thermal units are the ones that bring the binary variables. And why do they bring the binary variables? Because these power units, they have a discontinuous variable for the power production. The power production can be 0 or between a minimum and a maximum, right? And this brings a discontinuity into the problem. So for example, that means that for this thermal unit here, at time t is producing at this level, and this is the minimum and this is the maximum. So there is a binary variable for this discontinuity of or 0 or between the minimum and the max. Then there are limits on the ramp down and ramp up. That means that if you have a unit that at time t is producing at this level, in the next hour, it cannot ramp from this value to 0. That means that it has to ramp, for example, to this value, and in the next hour to the minimum, and then it can go to 0. And also, these units have minimum up and minimum downtime. So that means that you use the binary variables also for if you have a thermal unit that is a minimum uptime of 3 hours, you cannot have this solution like do not produce anything, produce, and do not produce anything in the next hour, because you have a minimum uptime of 3 hours. This is infeasible, so you need a solution like this. And the binary variables enforce this type of constraints of minimum uptime and minimum downtime. Minimum downtime means that if you turn off the unit, it must be off for 3 hours for a given number, right? And then there is another thing that is, when you schedule these units, that they are distributed, you have to schedule in such a way that if there is no wind, because the forecast is wrong, you need to be able to ramp up the units, right? So if you have a solution with 2 units and they are both at the maximum level, this means that you cannot ramp up the units because they are already at the maximum. So the problem or the solver has to find solutions like this, 3 units where they can ramp up because we have uncertainty on the wind and solar and demand. So we need solutions that allow us flexibility to go up and down. So what are the first stage decisions? The first stage decisions are when the unit is going to be on, all the units will be on or off tomorrow. And so we have a total scheduled power for tomorrow, right? And then the second stage decisions are how much reserves we'll have for each unit. And reserves means how much each unit can go up or down, the wind and solar spillage, and what are the power flows in each network. So that means that for this problem, we'll decide when it is on or off. And then for each scenario, we need to be able to be feasible in terms of the transmission network. So what means is that if we have a total power output for the next day like this, we must be able to get the right combination of units to go up or to go down. So the model has to determine for each unit how much reserves they are providing to the system for next day. And these are kind of our recourse actions in our model. So what is the formulation? So we have the startup and shutdown costs, the cost of the scheduled power output for the next day, plus the cost of the second stage decisions. And the second stage decisions are related with the reserves, upward reserves and downward reserves, wind and solar production, and the load shedding. And so this is how the formulation looks like. And this is subject to the power generator constraints, first stage, when they are going to be on or off. And the second stage power generation constraints are all related with the ramp ups and ramp downs, right? And also, yes, the ramp and the reserves. And then we have second stage power balance and second stage power flow constraints. So for each scenario of the wind, solar, and the demand, we need them to have a solution that it has a feasible transmission in the network. So let's go back to, this is the type of problem that we have, where X are first stage decision variables, and then the Y and the V are second stage decision variables. We have continuous. Here in this case, I have only continuous, just to show you what happens. So the decomposition works like this. What people do? What they do is they build a master problem of this formulation that I'm going to show you next. And then they divide those constraints for each scenario by subproblems. They solve the relaxation. We are minimizing the cost. We get a lower bound. We pass the X for each scenario. We calculate the upper bound. We check convergence, and we send all the dual variables to form an optimality or feasibility cut. We send this to the master, and this will cut the previous solution X. Okay, this is how Bender's decomposition work. Basically, it's like this. This is the master problem. These two are the cuts that we obtain values for these dual variables by solving the scenarios. The one problem for each scenario. And this is how the cut, in fact, looks for our problem, right? So this is the cut. And so here, let me see if I find the, yes, here are the first stage variables on the cut. So what we proposed, in fact, was something completely different. That is, remember that in the beginning, I showed you that the transmission network, the transmission constraints, the transmission network brings lots of difficulty to solve the problem. So what we did was the following. We pick all the constraints from the subproblems that are the constraints and the variables that depend on the uncertainty on the scenarios that are related with everything except the transmission network. and we copy them to the master problem. So we put everything in the master problem except the transmission network. And then we solve the master problem with those, but we leave here the network constraints. We solve the master, get X, solve the subproblems with all the constraints, check convergence. And what we are going to do is we are going to check in these subproblems which constraints for the transmission network are binding. And ones that are binding from the transmission network, we send them to the master problem. And with that, we cut the previous solution instead of sending the optimality and feasibility cuts. Yes.
Sorry, which problems you solve finding the basic feasible solution?
So these subproblems are LP problems, linear problems, because the binary variables stay in the master. And in these subproblems, they include everything that is related with the generators plus the transmission, right? But we send the solution X that was solved with the second stage variables and constraints of the generators, except the transmission. So this solution, this master problem, because it does not have the transmission network constraints, right? It provides a lower bound because not all the constraints of the problem are there. And then we send that solution to the subproblems that include all the variables of the generators plus the transmission, one problem per scenario. And we check which constraints we solve, and we check which constraints of the binding problems are, which constraints of transmission network are binding, and those go to the master. Okay, so we are adding information of the transmission network to the master on each iteration. So
Can I ask a question?
Yes,
Just
please.
to clarify, because there's something I'm not following.
Yes.
You said there were two stages, right?
Yes.
The first stage and the recursive stage. And still you said that there were like 1 hour per time step.
Yes.
So should we think that actually, because usually in scenarios, one thinks of this branching structure, right? You start with something and then you branch it maybe in two. Or...
Yes, but everything is in the, so all the time steps are in the same problem. So
yes.
Right. So when we say branch, all the branch and bound.
The randomness is the randomness that branches. I mean the scenarios that you're putting somehow for within those things like that, they were not branching. Right?
No, they are not branching because this is a two-stage also decision framework. So if we consider, and there is no market here, if we adapt this problem to an electricity market, you have the second stage that is what you are going, the reserves, but then you have all this clearance process for reserves.
I'm just tracking, it's very simple with the math.
Yes. Yes.
The randomness, right? I mean,
yes.
For example, the wind and the solar, right? They come as random. So normally I would think that, okay, you have like randomness that is coming into the system, right? And producing some kind of branches that maybe you have to prune later.
No. Yes. You may have, yes. You may have that if you have different decision stages. So if you have like 4 decision stages, right? You have one forecast of the wind, and then for the seconds, yes.
So
but
they understand that then therefore the second stage considers like
no. So for our second stage is just a sample of so what we have is a curve of the forecast for the 24 hours, and that curve is one forecast, and then there is another curve, but they don't branch. So we don't have like, if in the first hour you have this wind, then in the second you may have this, in the third, we don't have that. So
how does it make sense to have like in the first stage some curves that then later, you know?
Yes. So what happens here? This is a good question. So what we have is a forecast for tomorrow of the wind, right? And the forecast of the wind comes to us from Ibrahim, that is an ensemble of 50 forecasts for tomorrow, right? So you have 50 curves that go from hour 1 to hour 24, right? So we don't consider that if in the first hour you have this wind, in the second hour you may have this wind. So we assume that The forecast is one curve that goes from hour 1 to hour 24.
Yes, but when I take a decision, say I have to take an average with respect to the remnants, right?
Yes, yes, yes. So the decision is in respect to these different scenarios that may occur of wind, of these profiles of wind. Yes, yes, yes. And this is
Yeah, I still don't
okay. And
get
these forecasts are per node also.
Sure, but I mean,
Yes,
you know,
yes, yes, yes. No, yes, yes,
Well,
yes, yes. But what happens here is that we have like 40 profiles of the wind for tomorrow. So you want to take a decision of how your thermal units will be on or off based on these 40 profiles of the wind for tomorrow. And for each scenario is from hour 1 to hour 24. This comes from the approach from the stochastic framework, stochastic programming framework that we are deciding. That is, you have one scenario of wind that goes from hour 21 to 24. If you do some kind of dynamic programming, right, and that is a kind of, it will lead to a different kind of policy, and the formulation will be different. And in this case, you may have a wind that the uncertainty may branch on each hour. Yes, yes, yes. But in our framework, it is, each scenario is one.
It has some physical thing that, okay, you pick one scenario and now you can diminish with respect to it. You will follow that.
No, yes, but no, but you consider the 40 scenarios together in your original formulation, right? So you are taking one, you are trying to find one solution X that is feasible for the 40 profiles of the wind, of the solar, and of the demand. And then you, yes.
Yeah, but I mean, when you adapt the power given, right? You
No.
adapt to each of them somehow.
Yes, yes, yes. So
that actually you're following a curve that was defined from the beginning.
yes, 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 yes. And you have like 40. Yes, 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 yes. What in fact, in reality, people do, they don't consider this part of the different scenarios. What they assume is that the reserves should be 10% of the demand. That is what people do nowadays. They don't consider the stochastic part with multiple scenarios of the wind. So every day, so today they solve deterministic problems. And in fact, we have a problem going on with Hitachi, where they are not even at this level. They just want to solve their unit commitment problem in 15 minutes. No uncertainty yet, because they don't dream about that yet. Okay, but we can talk more. So basically, our idea was to move all the second stage information of the generators to the master and leave the power balance and transmission networks in the subproblems. And instead of adding cuts to the master, we add binding constraints of the transmission network that we find in the subproblems. So basically what happens is this. So this is the traditional master problem. And what we did was, to the master problem, we move some of these scenarios here that do not include the transmission network. And we leave the transmission network for the subproblems. So here is some details of the computational setup. So for this kind of system, the solution that we are looking for is the scheduling of this is the total coal generators, total natural gas, the nuclear, and the hydro plants for the next day, right? Let me show you some results. What we are going to show here, this is the Bender's decomposition. That is traditional, that is what the solvers do. This is the Bender's decomposition, but now we pick in two scenarios and we move two scenarios to the master problem. Right? It's still a relaxation. We are not including all the scenarios, just two scenarios, and all the rest are in the subproblems. And this is our proposed method with some variants, with cuts, without cuts, just some details. And here are the results. So with our Bender's decomposition that we implemented, like the solvers, for 8 scenarios, after 10 hours, we can do 2 iterations, and we cannot find any solution for the problem. the upper bound means a solution for the problem. If we add 2 scenarios to the master, after 18 iterations, we have a gap of 1.6, and this is the lower and the upper bound on the objective function, right? And when we use our method, now you get gaps below 0.1% here and almost here for a problem that we could not find a solution when we solve with the extensive form or using this Bender's decomposition, the commercial one. This is for 8 scenarios. This is for 20 scenarios. We can solve for this variant with a nice gap here, but there are some that we cannot. Okay, and so this is the gap. This is a very large gap. So in fact, this is what I'm running now on IBEX, different approaches to try to reduce this gap. But with this variant, in fact, after 10 hours, we can get solutions with a small gap. And this is what happens with the 40 scenarios. There are some cases that we solve well here, but there are some that we don't solve very well. So we are working on this now, how we solve that. And this is how the method, the profile of the method, right? So we see here that the first solutions of the master problem are quite fast. At the third iteration, we are below 1%. But then as you keep adding these transmission network constraints to the problem becomes more and more difficult, and it approximates the difficulty of the original problem. But even though we are already on gaps below 0.10%, this for 8. And I want to show you what happens with 40 scenarios, right? So in 40 scenarios, we add all the constraints of the second stage of the thermal generators to the master, and now the problem is huge. So it takes almost 2 hours to solve the first master problem with a gap above 1%, and more than 5 hours to solve the second master problem, but we get to a gap of 0.10%. So, and when we are doing this with 40 scenarios, what happens is that we are adding lots of constraints of the transmission, and then the problem becomes much more difficult to solve. But even though we get solutions that we could not before. So we were motivated to solve realistic case studies. The extensive form is intractable. The Bender's decomposition, that is the standard approach to solve these type of problems, is not efficient. And we try to propose an efficient method to solve this. In fact, the method that we propose, it is a mix of the method for the robust optimization and for the stochastic programming, because the robust optimization sends primal constraints to the master, and that is what we are doing also. So what we see is that adding scenarios to the initial master problems improves the tightness of the master problem. Adding all second stage variables provides a very high quality lower bound. And by adding this dynamic way of adding transmission constraints, help us to get lower gaps. And with this, I end my talk. Thank you.
Muito obrigado.
Foi prazer.
Temos a oportunidade de mais perguntas. No, I'm kidding. We can have more questions from the audience.
Hi, thanks for the very nice talk. I have a couple of questions if we have enough time. So the first one is regarding your formulation for the stochastic optimization problem. So as far as I understand, you create, you generate a lot of scenarios for your random variables, and you want all the realizations to satisfy your constraints.
Yes.
Right?
Yes.
I was just wondering if does it make sense to, I don't know, simplify the problem by, I don't know, maybe in a probabilistic sense, in the way that can you make sure just that, I don't know, 95% of the scenarios satisfy it?
Yes, I can. Yes, I understood the question.
Yes, so does that make sense?
It makes complete sense. So in fact, that is the approach that is used in engineering problems, right? It is a methodology that is called chance constraint, where you want your constraints to be valid with a given probability. And so that is used, for example, when you need risk control, but in engineering problems, right? So these constraints, 99% of the times, they will hold for this X solution, right? Here, we were more driven by the conditional value to risk, because the conditional value to risk is more linked with profits. But when you move to engineering problems, people think more on this, the constraints to be valid 99% of the time.
Okay, and
in fact, you write the constraint with the probability of this constraint to be valid greater or equal than some value that you define.
And in such cases, the solution scheme would
the solution scheme will
be
it will be different.
Yeah.
But at the end, we'll rely also on scenarios. But the formulation is somehow it is different, and conceptually, the idea of the risk is different because it's only those constraints. They hold 99% of the time.
Okay.
That is what people call chance constraint approach to solve stochastic optimization problems.
Okay. Can I ask one more question? Yeah, okay. I want to understand a bit more about the scenario generation.
Yes.
So assume there are like two random variables. Maybe one is the wind production and one is the electricity prices.
Yes.
Right. So maybe I have 20 curves of the wind power and 20 curves of your electricity prices.
Yes.
Does that mean that you do 20 into 20 scenarios?
Yes. So the scenario generation, it was a little bit tricky, right? Because in the first case, what we got was a forecast from Ibrahim Motaid that is an ensemble with 50 members, right? But then we wanted to go to 25,000 samples with 25,000 elements. So what we did there, we fit a KLE expansion, and then we sampled from the KLE expansion, taking into consideration the correlations on the wind. For the electricity price, what we did was the ARIMA model. We developed an ARIMA model. We fit an ARIMA model to the history, and then we have a model to forecast. But then we have your question. Yes, what we did was like you sample 20 wind profiles and 20 electricity prices.
Okay.
Which was different in the unit commitment. In the unit commitment, it is more complicated because you have that huge network, right? And so you have the huge network. So now how do you create the scenarios, right? Personally, I'm not interested on the creation of the scenarios. I'm more interested on the computational performance of the methods. But how did we generate these scenarios? What we did was the following. We choose a day that we want to do the unit commitment for the next day, right? And then what we did was we got the locations of the wind farms and the solar farms, and we are able to calculate what is the wind power and solar power for each wind farm for any day of the year that we want. So what we did was, okay, we are doing the forecast, we are doing the unit commitment for one Wednesday, and because these are many wind farms spread out all the time, so let's use the previous Wednesday, previous Wednesday demand and wind and solar power as one scenario.
Okay.
And in that way, we try to capture the correlation between the demand, right? Because the demand is related with the solar and the wind. And then two previous weeks, another scenario for each wind farm, for each node, because we didn't have, and we do the same for the future. Because that was the only way we thought about gathering these scenarios, keeping the correlation between the variables.
Okay.
And we had to go and calculate based on the weather conditions. We calculate what was the power output of the wind and solar, and we have the corresponding demand for each node of the network.
Okay. And was there like a general guideline on how many number of scenarios you needed, or?
So the guideline is how many can we solve?
Right.
That was the solution.
All right. Okay.
Yes.
Thanks.
Thank you very much.
Yeah. One more question?
Very nice talk.
Thank you.
My question is regarding how can
Yeah,
we
I
be
didn't
sure
forget you.
of the existence of even a single feasible point in these situations? Like, right,
Yes,
spending so much
yes,
time
yes.
looking for them.
No,
but there are
that
not.
is a very good question, because to set up these problems is very difficult.
Yeah.
Because you want to schedule what is going to happen to the next day, and you are giving a demand curve, right, and the wind and the solar. But in fact, one important aspect that people forget is what is the initial state of the system, because the initial state of the system may make the problem infeasible. But there is something there that we add, that is a variable called load shedding. And that load shedding is a kind of slack variable that you add to the system with a very high price, a very high cost. So if there is a feasible solution, there will be no load shedding in the problem. If there is no feasible solution, you find a solution with load shedding, right? It may happen. So and that indication of the gap will give you an idea. If you have a gap 0 or very close to 0, and you still have a very high load shedding, that means that there is no feasible solution. But these problems, they always account for some load shedding, and that means that you have to buy electricity from the neighbor state.
But that means that you solved the problem already. You found some
yes,
solution, then
yes,
you check.
yes,
It's
yes,
like a post
yes,
check.
yes.
But it's I don't know if it's possible a priori. In this case,
It's very difficult. It's very difficult. Sometimes to check if the problem is feasible or not takes as much time as solving the problem. Yes. That in fact is one option, that you are trying to solve the problem and you give an initial point. If the initial point is not feasible, for example, the solver will try to find a feasible solution, and that takes as much time sometimes as solving the full problem. So yeah, that is.
Thank you.
Welcome.
Shihab, you have a question. Could you please talk? You're unmuted.
Yeah. Yes. Do you hear me, right?
Yes.
Okay. Very good. Many thanks for the nice talk. I have 2 questions. The first question was partially answered. Just I want to make sure. So you are using forecast for the wind coming from weather variables. Like, I don't know, are you using like only the wind speed, or are you using more complex kind of model for the weather, and then you map it to the power forecast, like the wind or the solar? This is the first question. The second question, are you considering delays in the transmission system when you do the optimization, I mean, for the unit commitment problem?
Yes. Okay. So for the first question, yes. So what we did, for example, for the unit commitment, we got the wind speed and the solar radiation for the specific locations, right, for specific days, and then we use a power curve for a given wind turbine to map wind speed to wind power, right? And we do the same for the PV. So we get the solar radiation for that given location where the solar farm is. We go to a specific day in history, and we go from the solar radiation to the solar power for a specific PV. Okay?
Yes.
Okay.
Yes.
Good.
And the second question.
Yes, you have.
Yeah, the second question. Yeah, the second question. Yeah.
Yes, the second question was?
Are you considering delays on the transmission
Yes,
system?
yes.
Because this makes the maybe, I mean, the optimization also harder, right? I mean,
yes. So we are not
constraint.
considering delays, and we are not considering another thing that may be relevant. That is, we are not considering transmission losses.
Yeah.
And transmission losses may change a little bit this problem.
Of course.
The other thing that we are not considering, that is kind of the next step, is to consider that some lines may be off, and that is called the security unit commitment. That is very important, because you want to provide a solution that if one line goes off, the networks can still recover a state that is feasible and supply all the demand. That we did not consider also.
Thank you.
Thank you.
Any more questions, comments? I don't see anything else on the web either. So thank you very much. Obrigado.
Thank you. Foi prazer. Thank you.
That concludes today's activities. Thank you. See you tomorrow.